Professor Stewart, in this moment, is in streaming now.
Okay.
You could
Thank you,
start.
Shima. We can start. Okay. Welcome, everybody. Buenos dias a todos. Welcome to you all. You have joined the LAFMAT presentation today, and I'll just remind you about LAFMAT. We are a kind of a grouping of Latin American universities from Brazil, Peru, Colombia, Mexico, Chile, Venezuela, Argentina, Costa Rica, Ecuador, and El Salvador. Apologies if I've missed anybody off there. This week we have Akin from UCL in London, who will tell us about his latest research. He's on the flyer, he's been described as a doctor, but he's not a doctor yet. He is a PhD student and will be a doctor very shortly, I'm sure. But Akin is going to tell us about some of his research. So Akin, would you like to share your screen and start presenting? Thank you.
Okay. So as Stuart mentioned, I'm in UCL. I'm a second-year PhD student, finishing my second year, so I have some time left before I actually become a doctor. I will talk about effect of disorder potentials in quantized conductance. I will go through what quantized conductance is and some history related to it, and then some of the developments that happened in the field over the last couple of decades, and then motivate that to a kind of a simpler area of the field, how disorder can affect quantization. And I will show some like arbitrary disorder potentials effect on quantization. But before that, I will go through some of the fields briefly, because each of the points can go really, can have a very large depth. So I'll start. Before I start, I'm from Quantum Engineering Lab. We are a quantum transport group in UCL Electrical Engineering. And there's a picture of us from left, Joshua, Yingxi, Vivek, Sanjeev, which is my supervisor, Mandun, and myself. I showed some experimental data today, and Joshua and Yingxi, Joshua helped me fabricated some of those devices, and same with Yingxi, and Joshua led the EBL procedure as well, so I want to say that. And on the right, there's a QR code of our website, the general research that we do, publications, some fundamental information into electron transport can be found there. Okay, so I think a good place to start is thinking about resistance and limits. We all learn Ohm's law for physics of electricity at high school. And the question to ask is, what happens to these systems as length and width reduces to quantum limits? For today's talks, two limits are quite important in terms of length scales. One of them is width. When we talk about quantum transport, we usually talk about widths that are comparable to the Fermi wavelength of the electrons. And we're going to be discussing ballistic quantum transport. So that means that the length of the sample will be less than the mean free path. So it's not a diffusive process, it's a ballistic process where momentum is not lost. One of the initial consideration of these quantum limits famously is from Landauer, where he thought about electrons as waves and associated the resistance of a point scatterer to the reflection probability of that wave. And on the right, I have a picture of a very basic schematic of it, just a general idea. We usually have these large contacts where there's lots of electrons, and then they will be injected into a low-dimensional system where quantum features can be seen. So we will have these confinements, which I will talk a bit more in detail shortly, that will describe the transport phenomena. So there is these selectable modes, energy modes of the system that we will be interested in. The two-terminal conductance formula, Landauer-Bütschker formalism, is a famous formula where conductance is associated to fundamental constants, E and H, and also transmission probability. So I talked about these modes. each of those modes in the system will have a probability of transmission through the structure that we have, and that will affect the conductance. For example, even if there's no dissipation, that the electron in a system is perfectly transmitting, so there's 100% probability of that transmission, the quantized conductance will still be 2e squared over h, which is dominated by the contacts, that transition between the contacts and the region. And on the right, there's some data from Sanjeev's paper from 2021, or maybe a book chapter, where you see the conductance being in these steps. So this is what we are interested in. This is the quantization of conductance. There is a small shoulder here, which I will come to that shortly. Usually devices that I will be talking about today is they're going to be on heterostructures. I will also talk about them shortly, where there is an electrostatically defined confinement and electrons are injected in that one-dimensional channel. The experimental measurements of these systems are done at very low temperatures to see those quantum effects. And you can see that as temperatures increase in this data, this quantization smears out. So the temperatures can vary from tens of millikelvins to up to 4 Kelvin, 3 Kelvin that we would have in the laboratory. So within that range, usually some form of quantization is observed. So I will be talking about low dimensional systems, and I think it's good to talk about what that low dimensionality means. We can think about the density of states. For 3D case, we will have square root relation of density of states to the energy. In a two-dimensional case, there's an energy independent density of states. And in the one-dimensional case, we have this singularity. So it's inverse relation to the square root of energy. What is important here is that most of the systems that experiments will be looking at, and some of the simulations I will show will be looking at, are actually quasi one-dimensional systems. So an ideal system would have some form of confinement that is transverse to the direction of motion. And if that confinement confines the system in the ground state only, then we can talk about an ideal system. But once we kind of relax that confinement and we can get the higher eigenvalues into the system, the higher modes into the system, then I would say that that's a quasi low dimensional system. So quasi two-dimensional, quasi one-dimensional system. Early realizations of these systems are, I also think, that interesting to talk about, because I will also mention what kind of devices that we have today. But I think probably the most famous phenomena in the field would be quantum Hall effect, where the quantized plateaus are seen in a two-dimensional system with a high perpendicular field applied to the two-dimensional electron gas, and it got a Nobel Prize in 1985. The initial devices they used were inversion layer MOSFETs. So they apply some positive voltage, create the surface two-dimensional electron gas on a MOSFET, and then measure the Hall resistance and then later discovered the quantum Hall effect. I will be talking about one-dimensional systems, and the earliest realization I think of one-dimensional semiconductor system is using of these p-dop regions on the side of a accumulation channel, so that they would create a potential barrier and electrons would be squeezed in there. This wasn't a ballistic transport phenomena, so it didn't have any quantization, but it was the first experimental realization for a semiconductor one-dimensional structure, again, also on a silicon MOSFET. I did talk about these early devices, but today we have very high mobility devices that can show interesting phenomena where quantum energy scales are becoming relevant. The transport is ballistic, so it's super clean structures. And kind of going back to the dimensionality, I think it's always interesting to know and talk that we can create these low dimensional systems. Obviously, the world is three-dimensional. So the one-dimensional structure that I will usually be talking about and analyzing around today relies on a two-dimensional electron gas. And this two-dimensional electron gas can be created in a 3-5 heterostructure. The things I will be talking about today is on gallium arsenide and aluminum gallium arsenide. Aluminum gallium arsenide side of a heterostructure has a higher band gap than the gallium arsenide, so you will have the conduction band bending below the Fermi level. And it's grown by molecular beam epitaxy, which is the reason for such high quality of these materials as well. And there will be some dopant layer. There will be modulation doping, so silicon atoms will then donate those electrons into that well. So then we will have this well of electrons. So those electrons are now confined in the z direction, and then in low temperatures we can reach the two-dimensional ground state. So they're fully confined in z direction. They can move towards, so they can be explained two-dimensionally. Through electron beam lithography and surface gates, we can apply negative potential and confine this channel. So here there is a basic electrostatic solution where top gates would have a negative gate voltage, so that the electrons would see that as a barrier and then confine into that saddle point in the middle. And therefore we get a one-dimensional system, or quasi one-dimensional system. In the fabrication of these devices, it's quite generic steps. So a grower will grow the MBE process, and then experimentalist or fabricator will receive a wafer. This wafer needs to be cleaned, and then there will be optical lithography to create a MESA structure where 2-deg is selective. And around that MESA, so here you can see there's a hole bar here, so there's different parts. These are all 2-degs, and outside of this region, you don't have 2-deg, so there's no electrons here. Well, no 2-deg here, so conduction electrons. Then there will be optical lithography to build these larger patterns to deposit certain materials like gold or alloys. Of course, there's an order that matters for this, because there's ohmic contacts which needs to be annealed into the structure so that you can make a contact from the top and then reach the two-dimensional electron gas to inject the electrons. And in the middle, there are these tiny electron beam lithography defined gates, which are the ones that shapes the geometry inside the 2-deg when applied the potential on. Of course, it's not just a one-dimensional system you can create with this. There's various geometries, quantum dots, and etc. that people define as well. For today, I will just talk about basic one-dimensional systems. Then once these MESAs are defined and ohmics are annealed, EBL is done, which takes a long process. The structures will be split into the smaller pieces, and they will usually be put on a chip carrier and bonded to it so that it can connect to the low temperature electronics that the measurements will be made with. So I will talk about some of the developments in the fields in the last couple of decades, and these are this from a paper from Sanjeev. All of these things are super complex topics within themselves. Some of them are still open questions or debated topics. I will very briefly go over them because I think it will motivate the second part of the talk. In 1980s, integer quantum Hall effect and weighted fractional quantum Hall effect, I think, attracted a lot of attention to the field. And later, as I mentioned, 2D to 1D transition we're seeing in silicon. And after that, in 1988, with the higher quality heterostructures and EBL fabrication, that quantization that I showed in the second paper was discovered. And later to that, there was measurements of anomalous behavior or many-body associated phenomena in these structures. They are obviously, there's a lot of complex physics in these structures, and I will kind of talk about what these mean and what kind of anomalies that experimentalists would observe in their measurements, and then I will move on to what kind of fake structures that we can create with disorder that is similar to those. So when we talk about the kind of this many-body history of one-dimensional systems, one of the things to mention would be Luttinger liquid theory and the initial expectation of how quantization would collapse if a Luttinger liquid were to be existing in the system. there was a series of papers in early 80s and 90s that came out that expected some collapse of quantization, and to this conductance quanta modulated by the Luttinger liquid parameter. So Luttinger liquid is a bosonized description of these systems where one doesn't talk about the single electrons anymore, but collective density waves. And the prediction was that in a repulsive regime, so when electrons are interacting in those one-dimensional systems, one would see a reduction in conductance. And they were proposing that maybe if people had longer wires, such a thing would be observed. But later on, after the experimental attempts to see this, some associated phenomena, some reduction was observed, but this was attributed to backscattering in those long wires, and the expected reduction in conductance was not seen. And this was later explained by Maslow and Stone, that this charge density wave that the Luttinger liquid should have actually extends beyond the channel. And the conductance that we have, the 2e squared over h, where 2 stands for spin degeneracy, by the way, so that's for each spin channel 2e squared over h, is defined by the contacts, because the outside of the one-dimensional system is still a Fermi liquid. So, of course, we see a modulation to this conductance quanta in things like fractional quantum Hall effect, but this was not observed in these long wires as people initially thought. But there was other anomalies that are associated with many-body phenomena that happened as the measurements continued and material quality improved, etc. And the most famous one is the 0.7 anomaly. 0.7 anomaly is this shoulder that is observed below the first plateau, and it's repeatedly observed. Its origin is usually attributed to partial spin polarization and other associated many-body phenomena. It's still a debated topic. I think there is a paper here that I recommend, which is the paper from Bauer. It discusses one-hot singularity picture and how that can actually create, through the saddle point geometry, such a shoulder in the system. There's a couple of things that we know about these. So when we apply magnetic field in parallel direction, so we kind of create a Zeeman splitting, this smoothly transitions to 0.5, and it gets stronger with temperature, which is also an interesting anomaly. So usually these plateaus will smear out as temperature increases, but in the case of 0.7 anomaly, you can see it strengthen. So still one of the debated issues in the field, heavily discussed, still observed in most places. I think it's a kind of common point in the field that really commonly comes up. Another interesting many-body associated phenomena is the disappearance of the first plateau. So I talked about these split gate devices where you would have some lateral confinement into the two-dimensional electron gas through negative bias. And then people fabricated devices with PMMA on top of it and a top gate on top. So with a top gate, the overall density in that around the quantum wire that you create laterally can be reduced. And as the density reduces, the kinetic energy is proportional to density squared, whereas the Coulomb interaction is proportional to density. So after a certain regime, this Coulomb interaction will be a dominant force in the system. So that can lead to electrons transition from a single row picture to a zigzag and a two-row picture. And the idea here is that there was an observation that the first plateau disappeared. So the first ground state wasn't there in the conductance measurement, and instead the second plateau was there. I think it's definitely an interesting phenomenon. I am generally quite interested in, though this talk is not necessarily about this Wigner crystal regime, so-called, today. I think it's one of the most interesting phenomena that may happen in these wires. And it's also important for the later discoveries, because these low density systems was quite interesting for people. Interaction is quite strong. So maybe there is these Wigner crystal behavior where electrons are separated, and there is a lot of interesting dynamics here as well, like the transition from the two-dimensional region to the one-dimensional region. There is a lot of spin associated phenomena with this. So there is a range of open questions on how these can also impact measured two-terminal conductance. But yeah, this is one of the interesting phenomena. I think this was first observed in 2009 or 2010. So moving forward with this discovery, this observation, rather, people continued measuring these low density states. And at some point, there was observations of these fractional plateau-like structures. These are, there's actually Stewart in this paper as well, and Sanjeev, my supervisor. This is obviously quite interesting phenomena because in fractional quantum Hall effect, there is a very strong perpendicular magnetic field that leads to the fractional conductance that is observed. But in this case, there is no magnetic field. So this is not observed before. It's still, I think, quite open question. There is a theoretical explanation that explains some of the features observed, but to the best of my knowledge, there is no theoretical work that explains all fractions that are observed in experiments and also the associated phenomena. So once someone changes parameters like magnetic field and temperature to these structures, we know that they happen at low density regimes, and we know that they happen at various fractions. So explaining or studying these or trying to understand the properties of these low density states is definitely very interesting. And I'm talking about some anomalous phenomena so far. So we started with talking about Luttinger liquid expectations, not observing that, but then repeated observations of these 0.7 light plateaus, which are the shoulders below the first plateau that is observed. And then we talked about Wigner crystal regime potentially happening at low density when electrons start pushing each other sideways. And then we also talked about the fractional plateaus under no magnetic field. Another anomalous behavior can be created in the system due to impurity-related effects as well. This is a theoretical study from Tema, 1991, where they've analyzed what impurities or different conductance shapes can create deviations from conductance. So you can see some certain plateau-like structures or resonances. And this is an experimental study from Vivek, a postdoctoral researcher in my group, where they have seen correlation effects and mediated by disorder in these systems. I think an interesting result that they have observed is 0.7 light futures in the higher plateaus as well. I just want to show this also as an example in the field, something that I had measured over a year ago, I think. And it's again a two-terminal measurement of a quantum wire. And here there's a DC bias applied. So source drain potential is varied by application of DC bias. And there is some associated phenomena with this in the one-dimensional transport measurements. One of them is a structure at 0.25 of 2e squared over h, which means that there is both a spin splitting, so spin degeneracy is lifted, and also momentum degeneracy is lifted. So if we were to think about how the current is distributed, there is moving states in both right and left directions of that one-dimensional wire. And as one creates increase the potential between source and drain, then maybe momentum degeneracy can be split. And then we see these reductions in features. But the interesting part here is that, as you can see, there is not much clear phenomena here, because these results that we've observed, we think it's from a quite disordered sample. So we see a bunch of resonance behavior where there's peaks and unexpected phenomena. So this is a transconductance plot where the color represents gradient of conductance to the gate voltage. So that's the confinement and relaxing of that one-dimensional channel. And here there is the source drain bias. Usually in a plot like this, you don't see these negative gradients. So you don't see those peaks and kind of like dips and etc. And that is thought to be due to this disorder in the system. And most likely it is from that disorder in the system. So disorder in these devices can come from a very large range of things, and they can happen in fabrication process, like damages to gates or structure, or even the wafer itself. There could be the X centers in the dopant layer, so deep traps. There could be roughness in the interface of the junction. There could be background impurities, ionized impurities from the dopants, which we usually assume to be homogeneous at the dopant layer that I discussed before. But there could be inhomogeneities there, and they would have different effects. I will talk later about future work and how what I will now present can be improved, but there is a range of things. And usually in lab, when you have a direction or an idea that you're measuring and you see these things, you may not exactly know where it may be coming from. So one can observe hysteric behavior even in these low temperatures, parallel conduction, as I said, traps in various places of the heterostructure. So I'll talk about how we model like an arbitrary disorder into a ballistic system, but first I want to talk about a package that I use for some of the simulations. Maybe you've heard about it. It's called Quant. It's an open source package. It's a lovely package. So you can define a Hamiltonian, and the package allows you to solve for the scattering matrix. Scattering matrix associates the incoming modes to a structure to the outgoing mode, so the reflection and transmission probabilities. And as I discussed before, these transmission probabilities are directly associated with conductance. So I think the interesting point here is when we talked about modulation to the conductance quantum itself, that was a quantum effect. Whereas here, well, the quantum itself is being reduced or changed. Whereas when we have impurity or some disorder in the system, we are modulating the transmission probability. And the modulation to the transmission probability can come from various energy or potential structures in the system, which we will model by a arbitrary, we model here by an arbitrary function, but this can obviously be a quite like rigorous self-consistent function as well, which enters the Hamiltonian, and then scattering system can be solved. Then we can get conductance rates out of this. So the solution for this is obtained by the open source Python quant package. Before I talk about the more random disorder, which I will go through as several set of results, I want to show a result that we generated similar to results of the paper Hong et al. So they've studied such an impurity located at the front of the channel as well, and showed that how 0.7 like structures can be created only with an impurity. So if I go back slide, this Hamiltonian is a simple one-body Hamiltonian. So there is no interaction here. There is no Coulomb interaction. There is no exchange. We just build we solve an analytical Laplace equation, add some potential, and then solve for the scattering matrix and see how these transmission probabilities are modulated. And one modulation you can have with localized impurities at the bottleneck of that constriction is an evolution to a 0.7 like structure. Of course, it's not the 0.7 structure that is thought and mostly understood to be from many-body phenomena, but such a simple impurity can create that structure. So these results are from a paper from last summer that we had submitted for a conference, and you can also have wider impurities and have a bunch of these combinations that you can add to the system, which will create resonances and these 0.7 like plateaus. And I think it's quite interesting on exactly what can be created with non-many-body effect phenomena. And I will move on to that now. So what we did is that we took 300 different Gaussians. So we sampled uniformly for a range of amplitude of these impurity structures. I think we varied them from like a 20 to minus 20 electron volt, and then we combined them in continuous space and discretized it later on with the Hamiltonian. And then we look for different spreads, also uniformly sampled them, and then moved it through the constriction to see what kind of effects that it creates. Now, we did not study exactly what forms of physical impurity can create this. In terms of energy scales, we will solve the Hamiltonian at 4 electron volt, and I will talk about results ranging for a various energy scale. So more sharp impurities realistically would be closer to the channel, where the smooth ones would be further up, closer to gates. And I think when I talk about later work, what is interesting is if one maps out all of these potential impurity structures and maybe have a statistical model or something of that kind to understand exactly what can we observe experimentally in what limits, etc., and maybe combine that with some many-body inclusions as well. So what we did is that we have this randomized impurity potential. We use the same seed for each of these, so we move it to a different place of the channel. So this is a tight binding model. We define a 2-DEG, we define analytical gates, analytically defined gates, and then we move that structure in different places, and we vary the range of energy that we are sampling from, and then see what kind of effects that we get, how the wave function behaves inside that scatter, and what kind of anomalous behavior we can get from conductance. Before I start, I will show it in a brief moment, but we get a very large range of anomalous behavior. We selected some of them, and I will talk about some of them here. You can also, these are quite simple models, so you can create a different seed and different disorder, and you will also see plethora of effects. What I want to do is that look at these effects and what they look like and where they're coming from, and then motivate that for future studies. So this is a simulation where we have, as I mentioned, split gates, and we're going to reduce that potential. So we're going to include more and more modes into the system. And then as we have the modes, we have that disordered potential in the middle, and we look at how that disordered potential, as we increase the range of that sampling, what kind of behavior we get. So in the first case, where we are outside of the region, we get resonant behavior. And this resonant behavior makes sense because there's Hill and Bell-like impurities, so there would be a favorable energy for transmission to increase and then resonate and then go back to what would happen if there was no impurity or behave like in that trend. So here you can see those resonant behaviors. One thing we see that is quite interesting here is as you increase that range, we have this leftward shift. So this is also a transconductance plot where it's the gradient of the conductance to the gate voltage. So these red areas would be the risers, and the blue areas would be the dips, and the white areas would be the plateau-like structures. So we are interested in what kind of plateau-like structures or resonances that we can get out of this. And by the way, I should mention that these are offset curves. So we have offset them for clarity so that we can see each of the different curves. I think what's interesting here is that as U increases, we see risers start happening before. So this means that a Hill-like impurity may be more effective in that system away from the saddle point potential, allowing tunneling. Another important thing to mention here, I think an interesting thing, is that we see a plateau-like shoulder at 0.9 here. So in one of these cases, we see a 0.9 like shoulder, then it transitions into a normal plateau that happens at 3 milli-electron volts. Sorry, I think I have a... Right. So I'll do it like this for this slide. I hope you can still see it. So can you still see the slide like this? I can get a yes for this. That would be quite nice. Okay, so we move the impurity further into the structure, and from outside to inside, we see changes in the effects. And what we interesting to see is that the resonant behavior in odd or even plateaus differs in this case. So as we get closer into the saddle point, the impurity starts overlapping with the potential in the environment, and that will create different effects. So in the case A, this is much weaker. We see the center.
Sorry to interrupt. Your screen is moving around. Your presentation is moving around along your desktop.
Is it stable right now?
We mainly see your desktop image of the beach.
That is.
Try resharing.
I will reshare it now. Can you see it right now?
Still seeing the picture of the beach and the waves. If you try in presentation mode.
Can you see it right now?
See it now.
Yeah.
Okay, that's better.
Okay. So here there's an issue with my presentation. I'll talk about the effects that we observe from the conductance data. So as we move the disorder inside the structure, the superposition of the disorder with the confinement will change the nature of the effect. So instead of seeing stronger resonances in the middle, we will start seeing stronger resonances for higher plateaus. And this is because the density profile of different modes are different. So in the first mode, you have most of the density centered in the region, but the second eigenvalue it's spread. So as the Hill and well-like impurities and disorder can interfere with the electrostatic environment, and that can create different behavior for different plateaus in the system. So here, this means that there is a stronger off-centered variation in the potential compared to the outside case. Okay, my slides have a problem. So as the center of the impurity is moved further inside, the resonance structures can get absent or weaker. So instead, we see a much rapid suppression of plateaus. Again, I have the first case, and now we are quarter way into the structure, not at the bottleneck anymore, further inside. And in the first case, we had seen this really quick suppression of the first plateau, and here, slower suppression in the first plateau, and here we see it much more quickly. So as we get more to the center, this effect is amplified. Another thing that you can see is disappearance of the first plateau. And this is because in the saddle point, so in the middle, the energy, like the bottom of the energy profile of the structure is higher. So then when we add some Hill and well-like impurities there, the Hill-like impurities will make it even further up. So the first ground state will not form and transmit there. So instead, it will pass through continuously, but the second mode will be able to exist in the system. So if I were to not have a randomized disorder, but have a kind of smooth profile or a third middle gate or something like that, then I would see that jump to the second plateau quite clearly. You can also move it around and have different orders of those jumps as well. Also, you can see not only resonances in these systems, but also shoulder-like structures in different places, so in these non-integer values. I think another interesting point to mention here between these simulations and the experimental data is series resistance. So in experimental data, there will be some series resistance in the system, and that needs to be carefully taken out. Here we know what our transmission probability is, so we can kind of extract the conductance. In an experimental data, you could maybe have these different plateau-like structures. Then you should, in non-integer values maybe, then you should carefully understand what is the gap between each of those plateau-like structures to see if there's any suppression or not. And now I will move to like further inside the channel, which I think some other interesting effects are seen. Here, if you look at this image in the second trace where energy is 4 milli-electron volt, you can see supposedly some plateau-like structures. I will show briefly, but these are actually partial transmitting modes. So there is not only a single mode open in the system, there's multiple modes that are contributing to that conductance. When we move the impurity at the center, now the superposition of the saddle point and the disorder is quite strong. So we will see the auto plateaus getting affected further and further. And if we increase to really, really large values, we can see what I have discussed in the previous slide of the skipping of the first plateau. If I had to have if I were to have a smooth structure, this would be much more clear. And here the impurity is large enough that it is also quite clear that the auto plateaus are being skipped. And in the transconductance plot, you can also see this in the higher region. So you have the first plateau, you have a riser, then you have a plateau again, but this plateau is at 4e squared over h. So two of the spin degenerate modes that we have in the system. What I talked about with this 4 milli-electron volt trace is also shown here. So here in the zero impurity case, we have our riser, then a plateau, riser, plateau, riser, plateau structure. And when we increase the impurity range, the first plateau actually corresponds to the second plateau in the non-impurity case. So here you can see an image of the wave function inside the channel. So when we look at that first plateau at that split gate voltage, we actually see two modes partially transmitting in the system. And this partial transmission is quite important because if you don't have a shot noise measurement, then you wouldn't be able to separate how many, if there's two modes in the system or not. And in only two-dimensional experimental data, one may see a plateau-like structure, but that could be coming from multiple modes being in the system. And here you can see the second mode being affected by two modes in the system and a third mode trying to enter, and then the third plateau actually has 4 partially transmitting modes in the system. So I discussed about a simple model, and the kind of results that we can get out of this. If one does similar simulations, you can reach very, very similar results. You will see all these anomalous kind of behavior. I think what is quite interesting in the literature is there is not a clear rule book or an extensive research on what these disorder-related effects may be. There is explanations of them, and of course there's experimental methods where we can confirm some of them or not. But these experiments take very, very long times, and there is a plethora of anomalous effects that can be created with disorder. And what I think can be interesting is to improve these models, like sub-consistent, add those impurities, and then kind of, even though computationally quite heavy, generate a massive data set of exactly what kind of effects can be created. And later there could be models built on in similar things to guess the potential landscape of a conductance trace that is measured two-dimensionally. Yeah, and we can do some questions and discussion now and go back to some of these topics.
Okay, thank you. Muchas gracias. Thank you for your presentation. We usually have questions or comments first from the panel, the people that you can see on the call here. And then we have questions or comments from perhaps people watching on Facebook. So we'll start with our panel here. First of all, I'll just say thank you again for your presentation. We get many different types of topics in our LAFMAT. And I think this is the first time we've seen detailed one-dimensional physics described by you, so thank you. So in no particular order, as I see people on the screen, Henry, no questions from Henry. I was going to ask Henry first, but thank you, Henry, for your comment there. Could I ask Vena? Vena, do you have a question or a comment, please, for Akin?
Hello, good morning. Good morning to everyone. I would like to thank Sega for your presentation. It was very instructive also to know more about fractional effect and one-dimensional physics. I have one question about what is the range of disorder that one can consider as a perturbation, And
Yeah.
when the disorder becomes the disorder is so huge that the material is now considered a new phase into a new phase. What are the
Yeah.
range of disorder that
So I would
yeah.
say it depends on so simulation wise, it depends on what is the Fermi level that the system is solved in. So for us, it was 4 millielectron volts. And I think the most realistic impurity levels would be around that. When you think about gates create a much higher potential. So obviously the electrons cannot tunnel through those, but it would certainly depend on the Fermi level. And relative to the Fermi level, I think it could be interesting to see what levels of potential can exist within a system, but also what kind of things can be maybe manufactured or implanted into the heterostructure as well. I don't know if that makes sense.
Yeah, it makes sense. Thank you.
Okay. Let's have a look. The next person I have on the list is Carlos. Carlos, do you have a question or comment, please, for Akin?
Can you hear me? Can you see my comment too? Thank you, Akin, for the very interesting talk. I'm Carlos Rudamas from the University of El Salvador here in Central America. I was thinking about something fundamental. Can you consider this? I mean, you were considering as a model the one-dimensional quantum wire, let's say.
Yeah.
Could we use a, let's say, quantum well model in order to describe what you are studying?
Yeah. So
this is the first one. This is this after the second one. Yeah.
I think that so when you put these gates, you do create some potential confinement. So this system is quasi 1D, so there's multiple modes in the system, but one can, as you said, define a single lattice. So I think there is a work from Shushko from 2001 where he will consider a kind of like a circular system, apply some arbitrary phase on it, and then he will model the potential harmonically, for example. So it doesn't have to be a quantum well necessarily, but it can be harmonic, it can be a well, and that would depend on that confinement geometry, which I think is quite interesting as well. So alongside impurity, how that confinement geometry may affect the conductance, I think is also quite well studied. I think in Tekman paper they studied as well. But more simulations and more data can be generated with that. So definitely something like quantum well will be the confinement. In this case, it's just analytical solution to Laplace equation, but there is models with saddle well, harmonic oscillator, quantum well as well would work.
Okay, great. Well, the second question is concerning the type of disorder you are considering.
Yeah.
Have you explored the compositional disorder in your alloy?
No, I have an arbitrary function, but I think that would be super interesting to look at all different forms of disorder, a computationally very heavy model to kind of combine them and see exactly what kind of functions that we can create or have similar, like those, I don't know, superposition of Gaussian. So we can maybe parameterize a set of Gaussian superposing and then look at what kind of parameters would be associated with a real physical solution to the system, maybe gaining from computational and things like that. I think that would be definitely a next step kind of consideration. And there is various ones. So interface roughness would be interesting as well. Background impurities, all the smooth things that can also exist would be quite interesting.
Great. Hey, thank you very much for your answer and congratulations for your investigations in your PhD. Yeah, thank you.
Thank you, Carlos. We go down the list now to Augusto. Augusto, do you have any questions or comments, please, for today's speaker?
Hi.
Hello.
You are listening? Can you listen?
Yes.
Yeah.
Yes. Yeah. Hi. Nice presentation. And if I understand, the Coulomb blockage regime is out of your simulation. The simulation is purely ballistic. Okay. So this disorder, if I understand, may create some confinement in your device. So can you speculate about the Coulomb blockade regime together with ballistic regime? This maybe create the eliminating some plateaus. So the question is if confinement can be interfering in your system, or
Yeah.
can you talk about it?
Yeah, I think I understand. Definitely. So potential it's a confinement. It's
Yeah.
just a potential to the system. So for an Hamiltonian, you have the potential term, so it will just be ingrained in that potential. So you will have a Laplace equation or a self-consistent electrostatic solution there, and then inside it you put the impurities and what that function is. It depends on the way you study it, I think. Now, adding a Coulomb regime and interactions into such a system would mean that the simulation is many-body now, and it's not as easy. But I can again refer to the Shushko paper, where they look at a single mode, so only one dimension in the system, not quasi one dimension. They put a barrier, and then they introduce, through Hartree-Fock method, exchange and Coulomb. And with that as well, you can get anomalous disorder-like behavior. There is a single barrier, and they simulated. I've also recently simulated, so you can do a bunch of things with that. If you solve that like a more many-body kind of approximate method, you can also get kind of anomalous behavior to that 1D mode. But extending it to 2D or having such large-scale simulations may be computationally difficult, but it's something worth looking into as well.
Okay, nice. Thanks for your answer.
Okay, sorry, interrupt. Thank you. Thank you, Augusto. We had no further questions from the panelists. Henry and Alfredo don't have any questions for you. Do we have, Ximena, do we have any questions or comments from your community?
Good day, Professor Stewart. No, in this moment, we don't have any comments or any questions for the panelists. The people only say thank you for an interesting talk, for the knowledge about it. No, and for me, I only say thank you for the talk. No, we don't have any questions. Thank you, Professor Stewart.
Thank you, Ximena. James is not on the call anymore. Is James in control of any format for questions,
No.
Ximena? No, I thought so. Sorry.
No. No, is he or me?
Yeah, I
Don't
thought so.
worry about it.
Apologies.
Okay.
You would think I would know by now. I should ask a question myself, Akin. Although I'm the chairperson and chair people, generally speaking, don't ask questions. Could you just outline some uses, practical use for the technology that you have described?
Yeah. So if we end up having any form of quantum information in the semiconductor structures, then 2DEC and quantum wires can be a medium. Both some people propose it for computation, but also for getting that data from the fundamental devices. And I think from my perspective, especially regarding to impurity, I kind of like this analogy that I think to myself of how incredibly well studied we are for an airplane in the air, but how much more that we can simulate and understand for that quantum level, so that once we have technology that processes quantum information, or just generally low temperature electronics there and where quantum systems associated, I think rigorously studying these can be quite useful to understand, both from a fundamental and I think technological perspective as well.
Thank you, Akin. Okay, well, we just about finished, I think. Is there anything else that you want to say to the community here that's listening in Latin America? Any comments or other things that you want to mention?
I think the main kind of message that I wanted to have with the talk is, of course, like even for me, that research in the field will focus more on the many-body effects and all the cool things that happens that people find interesting. But I think all of the more boring things or redundant things can also have very interesting things, and it can actually help a lot of people. And creating and collaborating for simulations or experiments that may be measuring more of these boring things, quote unquote boring things, I think, actually helps a lot as for students or also early career researchers or people transitioning as well. So maybe I can say that I think I find a lot of value in that.
Okay. Well, that brings us to the end of today's presentation. So thank you, everybody. If you want to put your cameras on and say goodbye to the presenter today, that's also fine.
Thank you very much for your questions. Thank you for listening.
Thank you very much, Akin.
Thank you, everybody. Thank you for listening.
Thanks.
Thank you for the
Thanks,
talk.
everybody. Thank you, Ximena.
Bye.
Nice to see you guys.
Bye.
Thank you,
Have a
everybody.
good day.
Goodbye.
Bye, everybody.
Bye.